Hello everyone. We are about to get started with the live session. Few tips for the audience before jumping into the topics. You can adjust the video quality in the bottom right corner of your viewing window with the settings button. This session will be posted on YouTube as a YouTube video soon after the live session, so you can review the demo content and other presentation content afterwards as well. Also, feel free to chime in with your questions in the audience chat window. We will be covering a Q&A session at the end of today's topics. With these tips, let's get started. Welcome to today's session on MATLAB Speaks Hardware. Today's theme is focused on TI C2000 platform, specifically on digital power applications. We have two presenters today, Matt Pate from Texas Instruments and Antonin Ansel from MathWorks. We'll start with an intro to the TI C2000 product family from Matt, and then Antonin will take us through a hands-on demo on a DC to DC buck converter. Finally, we'll close the session with some resources and live Q&A. A note to the audience, you will enjoy this session the most if you're intimately familiar with either model-based design or the TI C2000 hardware platform. If you're a model-based design practitioner, the key takeaway for you is the TI C2000 integration and how you can use the capabilities for production code generation, whether you have motor control as an application or digital power. Whereas if you are a C2000 champion, you'll learn about the model-based design workflow and methodology. Now, I've used the term model-based design a couple of times. Let me go through it real quick. So the idea with model-based design is that a Simulink model or a simulation model is at the center of your methodology, and you use that model as the executable specification throughout your design and production process. Now you use the simulation to do rapid iterations and prototypes using designing with simulation, and then using automatic code generation capabilities from MathWorks, you can go to production with the same model that you used in the design phase. Of course, throughout this process, there's continuous test and verification being done with the system as well. The point is that the Simulink model is at the center of the methodology here, and that all entire tool chain is integrated under the single MathWorks environment. So with that quick introduction, I'm going to pass it on to Matt. If you can give us a quick intro to the TI C2000 product family.
Yeah, definitely. Thanks a lot, Anuja. And I'd like to thank everybody for joining us today for this presentation. So my name is Matthew Pate. I'm with the C2000 microcontroller team based out of Texas. Just want to give a quick overview on some offerings we have in power topologies, and then the direct products that we have that we'll be using today. So as you can see, we service a large array of power topologies, but also industries, whether it be AC-DC or DC-AC, but also DC-DC type converters, non-isolated and isolated, or just power factor correction on the back end. You can see very typical applications: solar power, telecom rectifier, server UPS, all those types of things, including charging pile for EV, HEV applications. The devices you'll see from C2000 MCUs are divided into two product families. One, you'll see here on the top, this the Delfino product line. That's our highest performance product line. It's available anywhere from, I think, 176 pin TQFP all the way up to 337 BGA, up to 800 MIPS. That's with our dual core C28X configuration, up to 1 megabyte of flash. We have up to 4 ADCs in 12 to 16-bit configurations, and up to 24 channels of PWMs. And the Delfino 377S is what you'll see featured in today's demo. The other line we have is our value line, the Piccolo class, from 38 pin to 100 pin TQFPs. Slightly lower performance than the Delfino line, up to 240 MIPS, with half a megabyte of flash, 280Cs at the 12-bit level only, and again, those PWM. So with that, I'll pass it over to Antonin Ansel from the MathWorks. We'll get into the demo. Thanks a lot.
Hi, everyone. I'm Antonin. I'm a development manager here at MathWorks, and I focus on embedded targets, including the target for TI C2000. So today I'm going to show a demo of a DC to DC buck converter. I'll start with the end, and then I'll show you how I got there. So here is the hardware, and I'm using today a LaunchPad from TI. It's a 28069M LaunchPad, which is connected to a C2000 DPS booster pack, which is a buck converter, which is connected to, which has two big power resistors connected to these heat sinks. So I will show how to control this buck converter. So here's my Simulink model that I generated code for, and today I'm using a companion model, which is a host model that will allow me to log signals as well as tune parameters. I'm having a problem right now. My laptop is about to die. So Anuja, if you could take over for like 3 minutes, I'm going to plug my my laptop power supply. Just give me 1 second.
Absolutely, Antonin, no problem. You know, that's why they call it hardware, because it's hard, right? So
I apologize. So I'm back in business. Sorry about that. I was here. I was seeing the warning. Okay, so let me take over. So the code is running right now. So I generated code for this this DC to DC buck converter controller, and the code is running. As you can see, I have an LED blink here. The period is 1 second, and it turns on for half a second, turns off for half a second. So my code is running in real time on the hardware, and I have the second model, which is just a companion model, which is going to help me log signal and tune parameters. So I'm going to run this model, and basically we can see live signals here on coming from the hardware. One thing I can do is right now I'm just asking for 0 volts, and the buck converter is not powered. So I'm going to switch on 9 volts to the buck converter. I'm going to start asking for voltage. So you can see that the voltage is going up, and I have a closed loop control with a PI controller. So eventually it's matching what I'm demanding. So I'm asking for 3 volts. Unfortunately, I can't display engineering units, because if I do that, I can't keep up with real time. So you'll have to do the math in your heads. 6.8 volts is 4,095 counts, and I'm asking for 3, so it's pretty normal to get little less than 2,000 counts. So you can see that I can, so my hardware is sending me a voltage measurement of what I'm asking for. I can add some active load in the loop by flicking this, and you can see that the current jumps up. There's a little bit of jittering, and you can start zooming. So let's do that. Actually, I'm going to stop this simulation, and we can start zooming into this region to see what happened when I introduce an active load in the loop. So you can see some disturbance. And this is real, actually. This is happening really on your hardware, and the data sent back to the host. So you can start, studying if that jump is acceptable to you, or if it's not good enough. In which case, you can start playing with your gains, add more P gains, add more I gains, and basically, I'm not going to play too much with this because of time today. But you get the idea. We have a way to monitor signals, and we have a way to tune parameters. Now,
right. So, quick question, Antonin.
Sure.
So with the parameter tuning, when you change the parameters on the model, it'll take effect right away on the hardware, and then you can see the resulting changes on the scope right here, right? So it's
that is correct. Yeah, so I'm sending values immediately to the target. I'm using a serial communication with the board, and that serial communication is going through the USB cable, and I'm running it at 12 Mbps. Now, one thing worth mentioning, the algorithm runs at 200 kilohertz, and I'm sending 2 data points, 2 UN16s, every 200 kilohertz, so that's 5 microsecond. So if you do the math, that's about 8 megabit per second worth of data that's going through that 12 Mbps connection. So I'm using quite a bit of this serial connection.
Now this the serial connection block, is it available out of the box, or you probably share these demo files? Is that so?
Yeah, so that's a good question. This block comes out of, if I'm not mistaken, it comes out of the instrument control toolbox. And so it's a serial host block. It allows you to read signal data from a Simulink model. And here, basically, it wouldn't be possible for Simulink to read one data point at a time. So I'm actually reading 12,000 data points, and 12,000 times 2, because I have 2 UN16s to read. So I'm buffering 12,000 of these 2 signals, and I'm reading every 60 millisecond. So if you do the math, that's 5 microsecond worth of data buffered into 12,000. So Simulink only has to read once every 60 milli. And Simulink is pretty good dealing with big chunks of data at slow rate, whereas your microcontroller is pretty good dealing with small chunks of data at fast rate. So if I can use that segue to jump into what's happening on the target, I can start with the communication channel. So basically, I have an interrupt here that triggers my PID control loop, and I'll show how this interrupt is generated. And here you can see the serial send. So this interrupt, you'd have to trust me now, but I'll show you that it's triggered at 200 kilohertz. So I read 2 ADC channels every 5 micro, and I do a serial send. And inside this serial send, it's a little complicated, but you'll realize that actually what it does is pretty simple. I have a counter that counts up to 12,000, and every 12,000, I'm going to go ahead and add a few ASCII characters, 4545 and 5353. These are the SS and the EE you see here. So basically, I'm sending data, and every 12,000, I'm just inserting, the start sequence and the end sequence. So I'm actually inserting the end sequence and the start sequence, the end sequence for the previous data and the start sequence for the new data. So that will help Simulink get synchronized with the data I'm receiving. So basically here, this serial send is just sending the two UN16s. Every 12,000, I'm just adding SSEE. I hope that makes sense. Let me jump into how this code is scheduled. So as many C2000 applications, we want ADC to be out of sync with PWM. You don't want to convert while your PWM is transitioning. That's to ensure that your conversion is clean. So if I look inside this PWM block, you will see, first let's see that the PWM period is set to 1,000 clock cycles. I don't have any divider here on this PWM module, so the PWM counter runs at the CPU frequency, which is 200 megahertz. So 1,000 counts gives 200 kilohertz, and that's 5 microseconds. So that's the PWM period. I have enabled my A channel, which is connected to the buck converter. So let me just quickly go to the schematic of the booster pack and the buck converter. I have these 2 transistors, and you can see that that's a bridge, and my PWM2A is connected to the upper leg, my PWM2B is connected to the lower leg, and basically if I turn this one on, this one has better be off, because otherwise it's a short circuit, so they have to run in a complementary fashion. And obviously it takes a bit of time to turn one transistor off, so you want a little bit of dead band, you know, for the time this one turns off before you turn this one on. So this is how I do this. So I enable PWM2A. When the counter equals 0, I set the output. And when it matches the compare A, when the counter matches the compare A, I clear the PWM2A. So if I pick an example, if my input is 250 counts, for example, it's going to be set for the duration of 250, and then it will clear for the remaining 750 counts. So I get 25% duty cycle on the upper leg. My PWM-B is turned off, but if I look at that deadband unit, I use deadband for both A and B, and it's set to be active high complementary. So the B is going to be the active high complementary of the A channel, and I use a deadband of 20 cycles to ensure that I don't have any shoot through or short circuit when I switch off my PWM-A and I switch on my PWM-B. Another thing worth mentioning, so the trigger. So from PWM, I would like to trigger my ADC, and I would like to do it in such a way that during the ADC conversion, I will not have any PWM transition. So if you look at the event that triggers my ADC, I set it to trigger the ADC when the counter is going up and is equal to compare B. So the compare value, the compare A is used for my duty cycle and is coming from an input port, so that's what's coming from my algorithm. And the compare B is set to a fixed value, which is the period value, 1000, minus 35, and that's about the time that it takes for the ADC conversion. So 35 clock cycles before the period, I'm going to launch a new conversion using my compare B value. And if I now open my ADC block here, which is going to read the voltage, the ADC is triggered by the PWM2 start of conversion signal and does the conversion, and at the end of conversion, posts an interrupt. And that interrupt is going to trigger this entire subsystem here. So via the hardware interrupt block, I've set it for ADC, and the ADC interrupt triggers this subsystem here. Now, another thing worth mentioning on the PWM block, the reload condition for the compare value. So the compare value reloads when my counter equals the period. So basically, I have one full period to run my algorithm, do my PI loop, send my serial data, and set a new value of the PWM. That new value is going to be taken into account when the counter equals the period, and as soon as that happens, I have a new fresh value that will be applied for the next PWM cycle. Another thing worth mentioning, there's another interrupt in this model, which is the serial receive interrupt, which is coming from my companion model. So every time I refresh I change a parameter. Basically, if I look inside this, I have some change detect. So basically, anytime we detect a change here, I'm going to trigger this subsystem on the host side. And on the host side, I'm sending a new serial message, which has 4 values: voltage demand, the active load, which is just a Boolean, yes or no, and the P gain and the I gain. So I'm sending these 4. It's the same concept. I wrap these with a header, so S and E. So I have some delimiters to make sure that the target understands the beginning and the end of the sequence. So I'm triggering an interrupt as soon as I receive a frame of 6 signals. And basically, Here I have a S, a E, and my 4 UN16s. So I'm going to receive an interrupt and feed that to the rest of the model. And here I have that GPIO to change the active load. And here I'm sending my 3 signals, voltage, P gain, and I gain, to the controller loop. If I look at this controller loop, so it takes my demand, voltage demand, it gets the voltage measured, so the feedback from the ADC, and I feed that into a simple PI controller. Here is the P gain, and here is the I value with the integrator. I have a limiter here, so if the controller goes a little crazy, this will guarantee that the output is within acceptable boundaries. That pretty much covers what I have here. Model-based design includes much more than what I'm showing here. I just showed how to generate code, how to monitor signals, and to do parameter tuning. Obviously, we have ways to simulate what the controller can do against the simulation of the plant. So you can use SimScape and put some resistors and run your controller algorithm against a simulation of the plant model to do your PI gain tuning prior to generating code. And we have a lot more activities around this. I'm just focusing today on the code generation, including hardware concepts like, you know, reacting on interrupts, setting PWMs, making sure that your ADC is in sync with your PWM, and showing how you can sequence all that on the target. Obviously, there's a lot more you can do with model-based design.
Thanks, Antonin. This was great. I was in fact going to ask you, the settings that you showed for the ADC block as well as the PWM block. I think those are closely decided based on the C2000 hardware platform. Whereas once you get that configured, the entire Simulink library of blocks becomes available to you. So you've shown a controller example here, but other blocks become available. And I think the point is to have entire capability, including the hardware settings as well as the algorithm, controller algorithm in the same environment, be able to do that.
Right, that's a good point. And yeah, I showed only 2 blocks, but obviously, so here is the Simulink library browser, and as part of this, we have support for all the C2000 variants. So today I showed the F28069M. So we have support for ADC, DAC, CAN, SPI, SCI, software interrupts, CLA. You can also offload some of the code of your main CPU onto the control law accelerator. And we try to be as complete as possible. This target is designed for industrial customers. We offer a lot of parameters on these blocks, and the goal is to go as deep as possible,
Right.
and give as much flexibility as possible to the target.
Right. I think it's a good segue into one of the audience questions. We can start taking the questions now. A question is, are there any other videos on MathWorks website, or where can I find more videos, like hands-on videos like these?
So that's a good question. There are motor control. I mean, motor control is very popular for people using the C2000 family of processors. We have a motor control video that goes deep into field-oriented control and how to program an F28027 LaunchPad with a Boost XL DRV8301. That's what I'm showing on my screen right now. If you search for MathWorks LaunchPad motor control and search for video, that should be close to the first hit. We have another more advanced video, which is controlling 2 motors with 1 controller, and that's running on the F28069 LaunchPad using 2 Boost XL DRV8301 booster packs. And there is a MIDI dyno setup that you can get from TI. So if you search for dual motor control, LaunchPad, MathWorks, that should be close to the first hits. And there's a full description of the hardware we use, as well as the technique to synchronize the two motors and make sure that you have the two sets of PWM running the two motors.
That's great. Thanks, Antonin. I think the next question I see is for Matt. Matt, they're asking about typical C2000 applications of the hands-on demo Antonin showed today, where they can be applied, as well as examples from industry where you've seen this type of workflow being used.
Yeah, no, that's a great question. And so one of the reasons we have this kit, this Boost XL buck converter, is because it's kind of a fundamental building block of some of the DC-DC step down that I talked about earlier. So some of the places you'll see this is in I'll get the feedback. Some rectification, whether it's buck or we actually have Boost demos as well, where we step up the voltage, but where it may be in a one application is actually in an onboard charger for an electrical vehicle, right? Where we're taking well, first we actually take the AC and convert that to DC, and then we step that back down depending on the voltage that's needed by the car's battery. And that's what you see a lot of times too with these step downs. It's really just taking, in Antonin's case, that 9-volt and stepping it down to something that you need at the local level, right? So whatever the main is giving you at that higher power level or at the higher voltage that you've transmitted, stepping it down, whether it be, like I said, EV, or it could be solar is another place where you step down the panel voltage, to go before you transform it back into the AC. So there's a lot of, like I said, between solar, like power supply or onboard charger, that's some of the typical applications. And you get some more exotic topologies. Like I said, the buck's kind of a very fundamental building block. You start to get in different, Vienna rectification, 3-phase Vienna topologies that are a little more complex and stuff that we offer, kind of those more advanced kits. But this is a really great starting point to kind of get into power conversion.
Great. Thanks, Matt. Maybe you can share some resources from TI website where people can go and learn about TI C2000 platform.
Hey, I see a question on, someone missed the beginning, but one thing I wanted to mention is the files that I showed today will be available on the file exchange, and once we post the video on YouTube, we'll put a link in the description of the video, so you can download the files and run it on your own hardware.
There's also a question about installation, Antonin. How do you install the C2000 support package, and what are the products needed for that?
So that's a good question. The TI C2000 support package needs Embedded Coder, as well as Simulink and the Coder suite. So I think you need MATLAB Coder, Simulink Coder, Embedded Coder. There are videos, getting started videos, that you can use to get started. But now the installer, so when you open MATLAB, you have an add-on manager. So if you click on Get Add-on and you click the support package, you type TI C2000, the instructions are very simple for you to get started. We require Code Composer Studio for the automatic download. We will not download it automatically for you, so you need to install Code Composer Studio on the side, and we will ask you where it's installed. The same is true for Control Suite. You will need that from TI. You have to install it on your own and pass the installation folder to the installer. So make sure you have that ready. and then just go through the installer and answer the questions, and it should be straightforward.
Yeah, one, just to add to what Antonin was saying from the TI side, with any LaunchPad, whether it be the 6.9 that he talked about in the DRV or the 337S we've shown today, any LaunchPad from TI.com comes with the complimentary full version of CodeComposer Studio. So there's nothing, and Control Suite's free to download as well from TI.com. So there, once you buy the LaunchPad ecosystem and the booster pack, there's really no more to it than that, and you just hook up your USB cable. And really, just to kind of elaborate on that, right, as Antonin showed, right, all the things he was doing was through that one port, through the USB connection to the PC, through the UART. So it's a really nice way, whether it be the scoping or actually stimulating that booster pack to kind of have a complete, system on your desk. And like I said, you get those software collateral for free with the LaunchPad.
Great. Thanks, Matt. I think we have time for one more question. I think they're asking what other hardware platforms are supported with MathWorks tools, and where can I find more information on that?
All right, so I can take that. Let me share my screen again. So on the TI C2000, we support pretty much all the variants. I think I showed you where to find information for the different boards. There is, if you type mathworks.com/hardware, you will land on this page, and you can go through the list of vendors that have MathWorks support. And I guess there are two ways we tackle hardware. One is live data streaming. We sometimes refer to this as MATLAB I/O or tethering mode. So from MATLAB commands, you can communicate with your hardware, get data from your oscilloscope or from your Arduino board. So that's the tethering mode, where there's no code generation in the loop. You're just communicating with the hardware using MATLAB commands. And another way to interact with hardware is via code generation. So in that space, basically, we generate code from Simulink model that we run in real time onto processors, DSPs, Linux-based system, FPGAs, PLCs now, and more. So we support a wide range of different vendors and boards, and that's the code generation way. So I hope that answers the question.
Yep. And we can look at the hardware vendors supported up in the drop down as on the same page, mathworks.com/hardware. So with that, I thank you for your participation. I think we are at the end of the session today. Thank you, Antonin, and thank you, Matt, for giving us a wonderful run through the TI C2000 capabilities with MathWorks tools. And we will be posting the YouTube video recording of this session soon on the MATLAB YouTube channel. So watch out for that. Thanks again. Bye.
Thank you.
Thanks, everybody.